Staying still with this idea of simple vectors, but going a little bit more general, so let's look at Euclidean vectors, because when we're dealing with just Euclidean vectors, then there are some things that we can tell, or some ways of finding out if a set of Euclidean vectors is dependent or independent, which is quite efficient and quite effective. So let's see how that works. So let's say that we have a set of vectors and that in fact they are linearly dependent. So that means that there is a set of scalars, not all of which are equal to 0, so at least some of them are not equal to 0, and this linear combination gives us the 0 vector. Okay, so what that means is that, as I said earlier, and as hopefully you have proved on the little exercise I gave you, that means at least one of these vectors is a linear combination of the others. Okay, so now let's look at this matrix. Let's construct a matrix V, which is obtained by using each one of these vectors as rows. Okay, so we're going to write each vector. Remember, these are Euclidean vectors, so each of them is written as a row. And I consider this matrix. Now, because these vectors are dependent, it means that one of those rows is a linear combination of the others. Well, what that means is that I can do enough row operations so that I can reduce that one row, that one vector, which is a linear combination of the others, to a 0 row. Since this is true, that means that the matrix V will have a rank less than K, because of course one of the rows is a 0 row, therefore there is fewer leading coefficients than K. It is also possible to prove, and I'm going to leave that to you as a little exercise, that the other direction is also true, namely that if those vectors are actually independent, then you cannot in fact reduce any one of those rows to 0, which means that the rank of that matrix V is actually K. This means that in order to check if a set of Euclidean vectors is independent or not, one way to do it is to set them as rows of a matrix, row reduce the matrix, find its REF, and then check if the REF is in fact has 0 rows or not, so if the matrix has rank K or not. And what we conclude is that the vectors are going to be dependent if and only if the matrix has rank less than K. If it turns out that the matrix has rank exactly equal to K, that means that those vectors are independent. But there is another way to check. Let's still stay under the same situation, and let's think about the fact that we have a dependent set of vectors. Okay, so there is a linear combination which is equal to 0 with numbers which are not all equal to 0. Well, in this situation, what we're looking at is actually a homogeneous linear system, right? You can interpret the left-hand side. This time we're looking at the vectors as columns, and we can think of this equation as a homogeneous linear system whose variables, however, are the CI's, and the fact that that equation holds, the fact that we're starting by assuming that the vectors are dependent, therefore that there are coefficients C1, C2, Ck that make that equation true, means that this homogeneous system has a non-trivial solution. In fact, it'll probably have many, or infinitely many, right, as we know from linear systems. Alright, so what that means is that if we look at the coefficient matrix A, which is obtained by thinking of all the vectors v1, v2, vk, this time as columns, and you may want to backtrack here. Look at this equation as a linear system. Okay, in this linear system, the variables are C1, C2, C3, etc. up to Ck. So these are the variables. These are the ones that display the role of the variables. Okay, v1, v2, vk play the role of the coefficients. Okay, so now we're looking at the matrix of coefficients v1, v2, vk, and we know that this system, we are told, has a non-trivial solution. So what does this mean? It means that the matrix of coefficients is going to have some free variables, otherwise it would only have the trivial solution. And again, the vice versa is true as well, and therefore we can conclude that if we write those vectors as column vectors, then the vectors are going to be independent if and only if this matrix A obtained by putting those vectors as column vectors has no free variables. So if it has no free variables, the vectors are independent. If there is a free variable, it means that the vectors are dependent.